Okay. Hello everybody. We start our lecture, and today is section 24.1, properties of power series. And let me recall, we consider power series of this kind, where Z0 and C0, C1, so on are complex numbers. And this object is called power series. Let me numerate it. So tag 1. And now I want to study properties of power series using Cauchy-Hadamard theorem or formula. So what Cauchy-Hadamard theorem and formula say? That if we denote such a number, but it may be not a number, maybe infinity, then we know that one converges absolutely for z minus z0 less than r, and one diverges for z minus z0 greater than r. That was proved during last lecture. So this upper limit always exists, either finite or infinite, and we have an agreement just only for this place, for this usage of ratio. 1 over 0 is infinity and 1 over infinity is 0, just for this place, nothing else. Nowhere else we'll use it. So now we'll use those facts to deduce further properties of our power series 1. And I'll start with direct corollary. Let me call it theorem 1. First, Adel's theorem. If one converges at a point Z1, complex point, then one converges for all z such that modulo z minus z0 is less than modulo z minus z1 minus z0. Proof. So one converges at Z1, Cauchy-Hadamard implies then what it implies. Let us think a little bit. Look, we know that for sure one diverges for z minus z not greater than r, right? And we know that one converges for z equals to z1. It means for sure that z1 does not satisfy this inequality, right? So it means that modulo z1 minus z0 is less or equal than capital R, for sure, right? But then, look, from those two inequalities together, right, what we deduce, the inequality from our theorem and that one, we deduce that for z minus z0 less z1 minus z0, we have modulo z minus z0 less than r, because z1 minus z0 is less or equal than capital R, right? And then by Cauchy-Hadamard again, we deduce one converges for those values of z. And that's all. So just a little reformulation, in fact, right? But it is quite useful. So once you know power series converges at a point, then for sure it converges at points with smaller distance from the center, center of expansion. Okay. Now, next theorem, theorem 2, uniform convergence of power series. If the radius of convergence of one is positive, r greater than 0. We know that capital R is always greater or equal than 0. And of course, it can be infinite, because infinity is greater than 0, I mean positive infinity, right? So, if the radius of convergence is positive, then one converges uniformly in the disk z such that z minus z0 is less or equal than r for any r in 0 capital R. So let me draw a picture to illustrate both theorems, in fact. So look, we have a center somewhere, and suppose we have positive radius of convergence, right? So what we know? First, Abel theorem says that if at a point our series converges, series 1, then it converges inside. And now we know even more. So if this is capital R, then take arbitrary smaller value of radius, little r, right? Then in this closed disk, right? The power series converges uniformly. Proof. Okay, take, and let's say Z1 such that Z1 minus Z0 is equal to R. Cauchy-Adamar implies that Cauchy-Adamar theorem implies that one converges at Z1 absolutely. Why? Because we know little r is strictly less than capital R, right? Hence, modulo Z1 minus Z0 is strictly less than capital R, and our series converges absolutely. What it means? Let me write down what is it. So, converges absolutely, it means that when I put modulus, so modulus Cn, and then I should put modulus Z1 minus Z0 power n, or Z1 minus Z0 is little r. So that is precisely this series converges. Now look, this is a real series, not functional series, just number series, right? And now, by Weierstrass test, we have what we have. So, modulus Cn times Z minus Z0 power n is less or equal modulus Cn r power n for all Z which satisfy this inequality, right? That is immediate, just reformulation. Modulo Z minus Z0 less or equal little r, so we have this inequality. And the series converges. So by Weierstrass test, we deduce that our series 1 converges uniformly in this disk, right? And that's all. And why it is important? It is important because of such a corollary. The sum of a power series, okay, not a, power series 1 with positive radius of convergence R is continuous in open disk. Proof. Take arbitrary R in between capital R and 0. Theorem 2, our theorem which we proved just now, we just proved, right? Implies immediately that what? Also, and sorry, one more thing, and Cn z minus z naught power n is continuous. In fact, everywhere, right? But what is important? Where our series converges uniformly. So, by theorem about how it is called, uniform convergence and continuity of functional series, there was such a theorem. So, if a functional series converges uniformly somewhere, then its sum is continuous, right? So, uniform convergence and continuity, this fact implies that we proved it for arbitrary functional series. So, if a functional series consists of continuous functions, and if it converges uniformly on a set, then the sum of this functional series is continuous on the set. So, the sum of our series, the sum of 1 is continuous in the domain where we have uniform convergence. So, on this, right? And now look, it's easier to understand geometrically, right? So, we have such a picture. For arbitrary little r, which is strictly less than capital R, we have continuous function on the closed disk, right? And this is true for arbitrary r, little r, which is less than capital R. Since little r is arbitrary, we have continuity everywhere in the open disk, right? Because take arbitrary point, for sure we can find such a little r which contains this point, right? Hence, the sum is continuous at that point. So, hence, because of r is arbitrary in 0 capital R, because of that, we deduce that the sum of 1 is continuous in the open disk now. And that's all. That's all. Okay. Now, oops, new eraser. Now, Theorem 3. Second Abel's theorem. Second Abel's theorem. If one converges at a point Z1 in C, then the sum of 1 is continuous on the interval Z0, Z1. What I mean by the interval? So recall that we are in the complex plane. So if we have 2 points of the complex plane, then what is this interval? In usual sense, right? The interval with ends Z0 and Z1. That is the interval. Okay? So now let us prove it. Of course, this assertion has a sense only when we have Z1 minus Z0 equals to capital R, right? Because if Z1 is a point inside the disk of convergence, then for sure we have continuity at a point, at every point of this interval, right? But now that is if Z1 is a point on the circle of convergence, then the assertion is essentially more is not trivial, I would say, right? So if we have a point on the circle of convergence, then that is an important assertion, and it doesn't follow from other properties. So how to prove it? Arbitrary point of the interval. Okay, I forget to write that we start proof. If we take arbitrary point of this interval, then we can write it as z equals to z0 plus t times z1 minus z0, where t is in the interval 0, 1. So we need to substitute into 1 those values of z. Is it clear that indeed that is precisely the description of points of the interval, that is not Z1. Okay, so we substitute. It means that the series 1 has the following form. So I substitute Z0 plus this one, and it means t times Z1 minus Z0 power n. And let me rewrite it as follows. Cn Z1 minus Z0 power n, right? And times t to the power n. Now, okay, rigorously speaking, we didn't prove Abel's test for convergence of complex series, right? Abel's test was proved only for real series. But in fact, the proof is the same for complex series. So Abel's test, what it says, how we use it here. So first, the series converges. Why? By our supposition. One converges at a point z1, right? So if we substitute instead of z1, then the series converges. And the second point is that the sequence t to the power n from 0 to infinity is monotone for any t in 0, 1, and uniformly bounded on 0, 1. Why? Because t to the power n in modulus less or equal 1 for all t in 0, 1 and n 0, 1 so on. That means uniform boundedness. So Abel's test, okay, of uniform convergence, I forget. Of uniform convergence. Convergence. Abel's test of uniform convergence. So Abel's test of uniform convergence then implies that the series converges uniformly on 0, 1, right? And what it means, converges uniformly. So okay, maybe let us use firstly Cauchy criterion of the uniform convergence. So what it means? For any epsilon greater than 0, there exists capital N natural, such that for all n greater than capital N, and for all p natural, and for all t in 0, 1, we have modulus of the sum from n plus 1 up to n plus p ck times z1 minus z0 power k t to the power k is less than epsilon. And now I preserve all other quantifiers except for the very last, for t, and I can rewrite it that for arbitrary z in the interval z0, z1, what is written here? Here it is written sum for k from n plus 1 up to n plus p ck times z minus z0 power k. That is precisely if you substitute this value of z, and this is less than epsilon. So what is underlined? What is underlined is precisely Cauchy criterion. Again, Cauchy criterion, that our series 1 converges uniformly on z0, z1. Z1. Okay. Z0, Z1. Closed interval. Okay. So, theorem is proved. Of course, there is a point. Yeah, when I gave you, there was a section remarks on complex series, right? I didn't give the detailed proof of Abel's test of uniform convergence, that it works also for complex series as well, but in fact nothing is changed inside the proof, because you have modulus and that's all, just modulus of complex numbers instead of modulus of real numbers. Okay, now there is a very nice corollary of this second Abel's theorem. The corollary is about absolutely different story from the first glance. And so, corollary. If the Cauchy product of two convergent series AN and BN converges, then the sum of this Cauchy product is equal to the product of the sums. So, remember that this corollary has a value when both series converge conditionally. We know I didn't give, no, I gave the proof, Merton's theorem, right? So if one of those series converges absolutely, then we know Cauchy product converges for sure, and the sum of this Cauchy product is equal to the product of sums. But in general, we cannot guarantee that Cauchy product of two conditionally convergent series converges. Both series might be convergent conditionally, but the Cauchy product may be divergent. There was an example, -1 power n over square root of n. We multiply by, we consider Cauchy product of this series onto itself, and it diverges. But it turns out that if we know that the Cauchy product converges, then for sure it converges to the expected result, right? Product of two series should be equal to the product of sums, right? And this is indeed true when we know somehow that the Cauchy product is convergent, right? Okay, so proof. I recall what is Cauchy product, so that is Cn, where Cn equals to the sum k from 0 to n, a k, b, n minus k. So, by the way, you see that for Cauchy product, I mean, that is not precisely the same formula which I gave to you when I gave the definition of the Cauchy product. Why? Because when we considered real series, we started from 1, right? Usually. And now I started from 0, and that is more convenient. You will see why. But essentially, what is the definition of Cauchy product? It consists of terms which are equal to pairwise products with the same sum of indices. You see, sum of indices is the same. And we consider all possible products, term by term products of those two sums, right? When sum of indices is the same. And we collect all of them. That is what is Cauchy product, right? Okay, now, what we know by the suppositions, what we know? We know that those power series converge at z equals to 1. That is the main idea, how to connect those two things. You see, we started now power series, right, function series, and now we return to usual number series. How? Just insert z to the power n. When you substitute z equals to 1, then these are precisely our series, right? So our supposition what says? Both series converge, right? And also the Cauchy product converge. So all of them converge at z equals to 1. Now, what is it? Now my watch is not precise. Yeah, okay, we'll continue after the break. Okay, we continue. the proof of corollary. In fact, this corollary of both Abel's theorems. So, not only of second one. So, what we know by first Abel's theorem implies that all those series converge for z such that modulo z less than 1. Because z naught here is 0, right? Center is at 0. And the first Abel's theorem says that if we have convergence at a point, then for sure we have absolute convergence, or absolutely. That is important for us. Absolutely converge for z such that modulo z is strictly less than 1, right? Second Abel theorem implies that the sums, I use the same notation for the sums. These are sums of those series. Are continuous on 0, 1. Now we need to understand that, observe, note that the Cauchy product of power series and Bn z power n is precisely our series, our third series. Why? Because what is Cauchy product? So let me recall. Cauchy product, I should sum up all terms with the same sum of indices, right? So what is Cauchy product? Terms of Cauchy product, indeed. Terms of Cauchy product, what are they? Terms of this Cauchy product are, what are terms of this Cauchy product? I should, look, sum up all terms with the same sum of indices. So akz power k times bn minus k z to the power n minus k. So look, I took k term from the first and n minus k from the second, right? That is precisely the sense of Cauchy product. Now look at this product. Z power k times z to the power n minus k. What is it? Z to the power n, right? common multiplier outside, and that is precisely z to the power n, right? And that is what is in brackets, precisely Cn, right? So indeed we have the Cauchy product, right? But now look, combine those two assertions. Look, we have absolutely convergent series strictly inside, right? And we know that product of two absolutely convergent series converges, right? In particular, Cauchy product, right? Moreover, the result is equal to the product. So, okay, where to write it down? That is not a good idea to erase what I am proving. So, from this follows, from the first Abel's theorem follows, right? Because of absolute convergence, we know that the sum of the product, right? Of course, also I should use this one here, right? That the Cauchy product is precisely Cn, right? So this is equal to the product of those two for which values of z? For z modulo z strictly less than 1. And in particular, for z in the interval 0, 1, right? And now look, in fact, 0 of course can be included, but doesn't matter. Now look, we have equality, which is valid for all z from 0, 1, but not at 1 yet. But we know that all terms here are continuous on the closed interval, right? Hence, this equality is valid for z equals to 1 as well, right? By continuity. And the proof is completed. The proof is completed. And this corollary is also important for summability theory. It gives a summation way. So look, if we want to sum up a divergent series, right, how we can proceed? We can consider such a power series, right? And if this power series has a radius of convergence 1, right? Then what can we accept? Okay, this series diverges, but we have sum, right? Then what we do? We take a limit, and that is, let me give an example how this summation that is called Abel Poisson summation. I'll not give details, but look how it works for an example of a divergent series which we considered before from 1 to infinity, sorry. N plus 1 over n, right? Oh, yeah, that one. For example, that one. Oh, simpler. Simpler, even simpler. This one from 0. Yeah, that one, right? We know this is, what is it? 1 minus 1 plus 1 minus 1, so on, right? Divergent series, right? That is divergent series. But look, we know this power series has a sum. Which sum? That is 1 minus z plus z squared minus z cubed, so on, right? And that is geometric progression, right? With denominator minus z. So 1 over 1 plus z, of course it's valid for z strictly less than 1, right? But look at the function. That is continuous function at z equals to 1, right? So this tends to 1/2 as z tends to 1 minus naught, right? In the real. Let me, so z is an r, otherwise I don't want to explain what it means. And what it means? It means we can give a sense for this sum, right? Let it be equal to 1/2, and that is called Adel summation process, or Adel Poisson summation process. And by the way, remember we had another summation process, Cesaro, right? By means, and it gave also 1/2. So there are at least 2 different processes which give the same result. Okay. Now let me give several examples to show that the behavior, as I said, the behavior of power series on the circle of convergence when it is equal to r. That is a rather complicated thing. It might be quite different for different, there are very different situations. So example 1 is most complicated. Example 1. Such a series, and from 1 up to infinity, z power n over n. Of course, here we should start from n equals to 1, right? N equals to 0 is not good. Okay. For radius of convergence, here we have Cn equals to 1 over n. Coefficients are real, in fact. For radius of convergence, we can use another formula, not Cauchy-Hadamard, but another formula, that one, which doesn't work always, but sometimes it works. So here it works, right? And what is the limit? What is the limit? Substitute 1 over n. Let me write n plus 1 over n. And what is it? The limit. 1, of course. 1. Radius is 1. Yeah. So we know by properties of by Cauchy-Hadamard formula, right? Once we know radius, we know that the series converges absolutely here, right? But now the question for z equals to 1. Surprisingly, but for our series, okay, converges for z equals to 1 without the point 1 itself. So you see that on the whole circle of convergence, we have precisely one point where our series diverges. Because we know, substitute here 1 over n diverges, right? That is, we know. But it turns out that it converges for all others. Let's prove it. So, proof for this. So z equals to e to the power I phi, where phi belongs to 0 to pi. That is precisely this set. So arbitrary point of the unit circle, except for one, can be written like that. We need to exclude 0 and 2 pi. E to the power 0 is 1. Right? Then z to the power n by De Moivre formula, that is cosine n phi plus I sine n phi. So the convergence of our series is equivalent to the convergence of two series, cosine n phi over n and sine n phi over n. This series we considered, right? Converges for all phi. In fact, we don't need to exclude this 0 to pi. But for cosine n phi, in fact, again, converges by Dirichlet test, converges by Dirichlet test, and let me give details. So once again we need to consider the sum k from 1 up to n cosine k phi. Let me multiply by sine phi over 2 and divide by sine phi over 2. Why we can do it? Because phi is not equals to 0 or 2 pi, right? Then phi over 2 is between 0 and pi, sine phi over 2 is never 0. So this we can do. Okay, we can use properties of trigonometric functions to replace it by that one. So that is difference of signs. Which signs? Sine of the sum k, I will write like that, 2k plus 1 over 2 phi minus sine 2k minus 1 over 2 phi. Sine of sum minus sine of difference, right? Over 2. But that is a telescopic sum. Because, look, how we can write down. Okay, I'll start with k equals to 1. Sine 3 phi over 2 minus sine phi over 2 plus so on plus okay, maybe k equals to 2, let me write down. K equals to 2 gives sine 5 phi over 2 minus sine 3 phi over 2 plus so on plus sine 2n plus 1 over 2 phi minus sine 2n minus 1 over 2 phi, right? And you see, so that is a telescoping sum. All intermediate signs are cancelled, and what remains? 2 sine phi over 2 times, okay, I will put it, sine 2n plus 1 over 2 phi minus sine phi over 2. In fact, that is very important formula. So usually it is written like, so you see what follows from this equality. I have minus 1/2, right? So I'll put this 1/2 to the left hand side, and it gives the following formula. And that is very important formula. We'll use this formula that is called Dirichlet Kernel. And that formula is very important in harmonic analysis for Fourier, trigonometric Fourier series. We'll use it, but essentially later. But for a while, what is important for us? Look, boundedness, right? So, what we deduce, we have an estimate k from 1 of cosine k phi is less or equal. I replace numerator by 2, 2 over 2, okay, cancel 2, 1 over sine phi over 2, let it be with modulus. Oh, no. Phi is between 0 and 2 pi, so it's positive, right? So, for arbitrary fixed phi, that is bound, right? And of course, 1 over n is monotone and tends to 0, hence Dirichlet test indeed gives us convergence, right? For arbitrary phi, strictly between 0 and 2 pi. Okay, so this example gives an example when we have convergence at every point except only one. Now, we can modify a little bit. Second example. Sum z power n over n squared converges on the whole circle of convergence. Of course, here once again r equals to 1, right? Because just take squares. By Weierstrass test. Because we replace by 1, right? And 1 over n squared is a convergence series. So here our power series converges everywhere on the circle of convergence, right? And another example, once again, slight modification. Again, radius is 1. Sum of z to the power n. Radius is 1. But now divergence on the whole circle of convergence. Why? By necessary condition or term test. Because if modulo z equals to 1, then z to the power n does not tend to 0, right? Z to the power n does not tend to 0 as n tends to 0 for modulo z equals to 1. That's it. Because modulo is 1, so it cannot tend to 0. So, you see, all possibilities may happen, right? Convergence everywhere in the circle of convergence, divergence everywhere in the circle, and somewhere diverges, somewhere converges. That's it. Of course, there is essentially more difficult question to describe the sets on the unit circle where power series may converge and may not. That is essentially more complicated problem. Okay. Now I have a little bit more than 10 minutes and maybe I think I can prove next theorem, very important. So, from now on, we consider real power series. And it means, let me change letters. Now all numbers are real. Of course, everything what was done before is valid for those series as well, right? But why now I don't want to consider complex series? Because I want to integrate and differentiate. And we don't know how to differentiate and integrate complex yet. So, I'll start with lemma. Power series, I forget, let me 2. Power series 2 and sum n starts from 1 up to infinity, n a n x minus x naught power n minus 1, let it be 3, have equal radii of convergence. So the radii are the same. Proof is very easy. So for the series 2, radius of convergence is 1 over upper limit nth root of modulo an, right? Now, let us compute the related upper limit for 3. here, that is, maybe I'll change slightly. Firstly, let me rewrite 3, rewrite 3, rewrite. How? Just replace n minus 1 equals to n to make it normal power series, right? That is sum m from 0 up to infinity, m plus 1 a m plus 1 x minus x naught power m, right? So then what is I'm afraid that I've been not able to prove. Okay. So let us write upper limit. Okay, let me, that is R2, right? And then what is R3? Radius of convergence for 3. That is 1 over upper limit as m tends to infinity, mth root of m plus 1 modulo a m plus 1, right? But now look, I can compute this limit, m tends to infinity, mth root m plus 1 modulo a m plus 1 as follows. That is upper limit mth root of m plus 1 times what? Times m plus 1th root of a m plus 1 power m plus 1 over m. Okay, now look, we know that upper limit of this, okay, how to say, upper limit of this is equal to 1 over r, right? R2. 1 over R2. Why? Because we have the same sequence as here, but instead of n we take n plus 1, right? It is precisely the same sequence, hence it has the same upper limit. Now look, if we take arbitrary subsequence of that sequence, right? What we know, if it has a limit, then the limit is less or equal to that one, because that is large, right? And look, if we take this power tends to 1, right? Hence, arbitrary subsequence, convergent subsequence of that sequence has the same limit as corresponding subsequence of this sequence, right? And it means that the upper limit of that one is also 1 over R2, right? Now look, so we know we have a product. What is the limit of the first term of this product? As m tends to infinity. I can write as, okay, let me write mth root of m plus 1 equals to m plus 1 power 1 over m, or e to the power 1 over m times logarithm of m plus 1, right? So we know the exponent tends to 0 because the logarithm tends to infinity slower than 1 over m, right? Slower than m. Hence, the limit of exponent is 0, so it tends to 1. Tends to 1, right? This tends to 1. So, look, take arbitrary subsequence of that sequence. Partial limit is less or equal than that one, and we have a subsequence with this limit, right? But arbitrary subsequence gives convergent subsequence of that one, right? Because we have product of two sequences. So the upper limit of this one is also equal to product 1 times 1 over R2, and it gives 1 over R2, right? So in fact, radii are the same. Radii of convergence for 2 and 3 are the same. And what is 3? Let us look carefully. How it was obtained? We differentiate term by term. Series 2, term by term, we differentiate in x, right? That is, the series 3 is the result of term by term differentiation of the series 2, right? So the lemma says that radii of convergence of the series and of term by term differentiated series are equal, and vice versa. So, I mean, if we have a series, we know that differentiating preserves radius of convergence, then integration also preserves radius of convergence, because integration is inverse operation, right? So we can, if we integrate, then we differentiate, and it gives the same radius of convergence. So what follows from this lemma, that term by term differentiation and term by term integration give power series with the same radii of convergence. That is very important assertion, and it seems I'm not able even to formulate the theorem. It should be last theorem in this section, but somehow I was not able to complete. So maybe I'll make a precision of the title, Properties of Power Series. Convergence on the circle of convergence and continuity. So what I was able to give today was just related to those two topics. I wanted to cover also differentiation and integration, but unfortunately not yet. We'll continue tomorrow. Thanks for your attention, and that's all.